All right, so welcome everybody to the webinar. Welcome, Daniel. Let me just quickly. Yeah. Maybe let's kind of start by introducing everybody to the Zoom platform a bit. Basically, we have the Q&A section as well as the chat section. So you can, if you have any questions, you can put them in the Q&A, and then either us or some of the other moderators will answer them. And then also, you can also use the chat and talk to other people there and talk to us there as well. Let me quickly close this. All right, so maybe the way we can get started is we can at first kind of do a small introduction, kind of talk about who we are, what do we do. So Daniel, maybe you can start with yourself.
Yeah, let's move one screen forward just to do a quick just see where everyone's going. And so yeah, we'll do introduction and then we'll talk about LiDAR, do some planning considerations, go into workflow, some flight planning with UgCS, and then some automation and terrain considerations. And then next slide.
Yep. Just
trying to hold us into the structure we set up. Perfect. So hi, everybody. I'm Dan Aber. I'm the CEO of Modus, who's mapping operations and data. What we basically do, we're a full service mobile geospatial solution provider working in construction, utilities, and environmental industries. And how we actually got started, or how we actually operate, is most of our employees have been in the drone industry for well over 20 years. I actually started in this industry being a military attack helicopter pilot. I had just finished off a Top Gun tour and teaching other people how to actually fly helicopters. And I was asked to go to Central Asia to command several UAV units, and how do we actually use those. So that was back in 2008. And then that's really what formed what we see for Modus today, and how do we actually use an unmanned aerial aircraft to collect information and actually put it to good work, mostly in the geospatial is where I like to focus. And then we fast forwarded into about 2014, when I was a program manager at General Atomics, overviewing different projects for Reaper and Predator, which is a very large drone for different countries. And that's when we started to say, hey, it's time to move into the commercial market and take the technologies that we've been developing for the last 20 years and move into the space. So what we essentially do for our clients is accelerate them. And what I mean by that is we accelerate their workflow, we reduce the amount of errors that they do, we increase their safety, particularly around LiDAR and data fusion and decision-making products. So that's Modus in general, or in a nutshell, if I haven't gone too far.
So let's save a bit for later as well. So about us, SPH Engineering, basically we are the developers of UgCS ground control software. So you're going to see the software later as well. If you haven't yet used it, I assume maybe some people here are new to it. Maybe some of you have already used it. And so what UgCS does is it allows you to plan drone missions in a 3D environment. And also it's not really limited. It doesn't really limit you to one certain kind of drone. So this means you can use drones from DJI. You can use drones that have the Pixhawk autopilot. So it just offers so many opportunities. And this is why we kind of, connected together with Daniel, because it also offers to use LiDAR as well on drones. And this is what it's all about. So we're going to cover both. We're going to cover using LiDAR as well as planning missions.
Excellent. Excellent.
Yeah,
all right.
So maybe let's move forwards.
All right. Well, before we actually go into how do we use flight automation, we really have to start with a few of the basics. And for today, I would like to do something a little interactive, so that everybody can kind of see what everybody else's experience level is. And so what I'd like to know right now is how many of you folks have actually used LiDAR, and how many of you guys are actually looking at LiDAR or have been using photogrammetry. So if you want to write that in the chat, whether you want to type in yes for LiDAR, or you want to type in photogrammetry, or just looking. That way everybody can kind of see, the wealth of experience of the people that are attending today. So, what is LiDAR? And I'm not going to go into, it's a very complex topic. So I'm only going to cover it in a very broad brush, high viewpoint. But if you want more information on this, we'll give you a link to what we have as LiDAR University, and we have a free course in there. It's about 4 to 5 hours long that go into it more specifically. But let's cover the high points right now. So essentially what LiDAR is, light range and detection. And how that essentially works is we're using light, in this particular case lasers, and we're sending out a signal, and that signal is being timed, and then it's going to have some kind of reflection off of a body, and part of that energy is going to return back to a sensor on the on that piece, or on the on the sensor, excuse me. And so that's the essential premise. And so we call this kind of collection modality a active sensor. So some specific things that you need to understand about using an active sensor is that, especially when you're moving, is that you need to have GPS, and you need to have some kind of inertial or acceleration measurement device. So that joining of a inertial measurement unit and a GPS is called an inertial navigation system. And that is really the heart of that system. And so as you're moving through space, that inertial navigation system gives that LiDAR data a reference so that you can move around, and and you don't have to use quite as many ground control points. So that's essentially how that piece works, and that's going to be important as we talk more about LiDAR in the planning. And a lot of the stuff that we deal with planning is going to be around not so much the LiDAR as much as the inertial navigation unit. Now, if everybody, in comparison, we have photogrammetry, or we call structure through motion. And how that works is you can still have an INS, or inertial navigation system, but a GPS will be sufficient. The difference is that the light source is coming from somewhere else, and you're very light dependent, where LiDAR, you're sending out your own energy and you're getting it back. With photogrammetry, you're getting it from somewhere.
So technically, you could what you could also say is that in essence, you can also do LiDAR missions in the dark. I mean, if you wanted to.
Absolutely.
But with photogrammetry, you're kind of limited to on the natural light source, and so obviously, when you fly with drone at nighttime and take pictures, you're not going to see anything. But LiDAR, you're still going to get this data.
Absolutely. And matter of fact, a lot of times, depending on what your application is, it's actually better to do it dark, because if you're doing urban terrain, or where you have populations, airports are a great time. You do an airport after hours and you have it mapped where you can't do that with photogrammetry, and you don't have all those people that you're dealing with. Also, you don't have cars and that kind of thing. So yes, exactly. We're not limited by day or lighting conditions. But the other thing with the difference here is with the passive sensor, your heading is much, the camera orientation is not as important. So as you're flying, you could have that camera turned off to the side, or whatever, or forward, or an oblique, or in the nadir. It doesn't really matter, because what we're doing is we're stacking images over top of each other. With LiDAR, on the other hand, the orientation, once you take off, has to be fixed. And that has to do with, because it is the reference point, where with a passive sensor, we're going to use a ground control point to give it a reference. And so that's the biggest difference between these two technologies, is that we can use GPS points on a picture, but we stack pictures, and then we have to give it a ground control point to give it reference, actually several of them. Where with LiDAR scanning, we were actually using the INS as the reference point, but we had to be much more precise on how that sensor moves through the airspace. The last comparison I'll give is that, that when you're doing LiDAR scanning, that is a data table. So every LiDAR pulse that goes out and comes back is going to be a referenced three-dimensional point, where with photogrammetry, we actually have to do this in post-processing. So with LiDAR, you're going directly into, it's direct data, and therefore it's very forgiving in how quickly you can manipulate it. But on the flip side, photogrammetry is cheaper, but you're only going to collect the outsides of things, where with LiDAR, you're going to actually penetrate and get structure from underneath.
Right. So for example, if you fly a photogrammetry mission over a vegetated area, such as, let's say, a forest, then you're not actually going to get the terrain data. I mean, you're only going to get the treetops. But with LiDAR, you're actually going to get the ground data.
That's correct. Depending on, again, how dense light has to get through, both for photogrammetry and LiDAR. The biggest difference is with LiDAR, that beam, and you'll see this in following slides, will hit one leaf, part of it will return, and part of that light will keep on going for the second or third or fourth return, depending on your sensor. And that's what provides that structure that we're talking about, especially with vegetation. Good question. All right. And again, if you want to know more about this, we'll put a link in for lidaruniversity.com to really, which goes into much more detail on this sensor head. We move to the next slide.
Yep.
Okay. So now that we actually understand the basic premise, we're going to go a little bit into some initial planning factors that before you even come to UgCS and you're actually looking at a job. And a lot of the consulting that we do is about how do you take this technology into the job or the workspace, and how do you do a bid. So the first thing we have to consider, out of all this criteria, is the coverage area. And what I mean by coverage area is, okay, how much area that you're going to, how expansive, but are you going to be doing things in hectares, or are you going to be doing geocorridors and that kind of stuff? Because that's going to change a little bit of how you're going to want to lay out your design, and how you're going to actually pick up the topography with your sensor. The next thing that you look at is actually the topography and the elevation differences. And I'll talk about this picture in particular in just a minute. But if you were just doing agriculture over flat fields, well, then any software will do. And what's nice about UgCS is, and we'll cover this a lot, is the terrain matching or the terrain follow feature that a professional photogrammetrist or a professional LiDAR person needs to get access. And you'll see why you want to stay even over the terrain as we go farther on. The next piece of this that you want to look at is the vegetation. And vegetation for LiDAR planning, one is for the sensor head, which I'm not going to go too much into detail now, but the second part of that is for flight planning. And with UgCS, we're getting DTED or elevation information from a GeoServer, but it's really important to kind of understand, what kind of vegetation you're dealing with, what's the heights. Like for instance, here in San Diego, the average tree height is maybe about 20 to 30 meters. But if I go to, let's say, Michigan or up into British Columbia, but now you're looking at maybe 50 meters, 60 meters. And so you have to account that in your planning factor. And the last thing, which is when we do any consulting or we're looking at a use case or doing a bid, is the data requirements. A lot of folks, when they buy LiDAR the first time, or the LiDAR system, or they're looking to do this, they really don't understand, what that data is going to be used for. And so when you're planning LiDAR, it's important that you understand what it's being used for and the software flow, so that you can actually, when you're in the field, you're collecting it correctly. Because
can you maybe give an example of one data requirement versus another one, and how that might impact how you're actually doing the scanning mission?
Correct. Okay. So, that's a great question. And as an example, let's see here. So if I'm doing just general contours, okay, and my contour level is, let's say, 2 feet. At that point, having 400 to 800 points per meter squared makes no sense at all. because you only need a few of those to actually get the only a few points to get the terrain, and these LiDAR points actually serve as survey points. So if you're packing your points so closely, or your density so close, you have a lot of wasted data that you have to go through. And where on the flip side, if you are doing, let's say, forestry, or you're trying to do building feature extraction, now density becomes a real must, where you want to get the features in the corners and in the windows and those. And so knowing those different data requirements is important. I mean, as an example, I was working a contract for PwC, and we're working a utility company. And I asked a very innocent question. They had showed me a slackline measurement, and I asked, well, what kind of point density do you need, or do you require? And they thought, like, oh, you're off to get the secret sauce. But no, what it came down to, and why I was asking that question, was that, I'm trying to get a 3 centimeter line, which is metal, which gives me a higher return. But if they required, let's say, 30 or 40 points per meter squared, I would have to fly slower, lower, and more deliberate over the structure that I was trying to pull out. Versus if they only needed 3 or 4 points per meter squared, now I could fly higher and faster, and that means I save a lot more time in the field, and I can cover more area. So I can bid lower, or I'm looking at a better margin. So that's the difference in why data requirement is so important, because it's going to change everything that you're going to do in the field in your collection.
Right. So LiDAR, it's always kind of you have to find the right balance between the point density as well as the area that you want to cover.
That's correct. And the other thing to consider also, we talked about vegetation, and we'll see here in a few minutes. I can show you how much energy is going to go out of the sensor, but it's also kind of knowing how much energy you're going to get returned. So with vegetation, you're going to get less return than you would with bare earth. And some of that you're going to have to learn with some experience, but just to even know that, okay, right now I'm doing aggregates. And so I'm going to be dealing with brown stone, I'm going to get an 80% return. Well, once I go to, let's say, full leaf vegetation, now I'm looking at maybe a 20% return. So that has to be part of that planning consideration in your data requirement. And I'd like to finish this slide really quickly with the graphic that we have here, because I think this was a real testament to what we did. So this right here was a rock quarry that we did, one of the first LiDAR companies that we supported. This was with a VLP-16 on an M600. And what was neat about this is, so we had, I think this was about 20 acres. The terrain and relief area here was about 300 feet. So that's about 100 meters or so of actual elevation change that we actually had to deal with. And we had vegetation on the hills, and then we had aggregates that we had to deal with here. We actually completed this collection in less than 20 minutes, with about a 10-minute setup time beforehand. The data we got off the machine was about 20 minutes later, and then we actually had aggregates within another 20 minutes. And by the end of the day, we had contours, DEMs, vegetation management study, all of this done in less than a day. Where, if we had been using a traditional, we'd be flying really high, we would not have got the point densities to allow this. So this was a 450 points per meter squared job. And so it really turned out to a testament of sold me on how you can take a small sensor and make a lot of money and be very efficient, and even operate safely in hard areas.
Some people are asking, actually, so what sensor are you using, let's say, for this instance, if you remember?
This one, again, was the Velodyne 16 on a with an INS setup, and we post-processed in PPK, or post-processing kinematic, which again we'll talk about, or I'll refer you to a source to tell you about how you do your corrections. But yeah, that was the sensor. So probably one of the most affordable on the market right now, and one of the ones that we, well, let's just say it gets you the highest return on your investment. So very capable sensor for what it is. Next slide.
Yeah, all right, let's move on.
Okay, so we talked briefly about data requirements, and we talked a little bit about in that story about, hey, how many points per meter squared that you need. So that's probably the first thing that I look at when I'm trying to determine my flight profiles is, okay, how much area can I cover? And then how many points? And so with every sensor that we have, and we kind of have a mismatch here. I mean, the pictures that you're seeing on the left is actually a Regal Minibux, and the right is an HDL32 data set. But for the purpose of understanding the planning part of this, you know, an HDL32 puts out an enormous amount of energy. It has 32 lasers in its array. And so you can see that you can attain over 900 points per meter squared, you know, with perfect reflection. But this is going to change, and I'll talk more about why that changes in a minute. It's going to change based on two factors, and those factors are going to be how fast you're actually going to be moving over the ground. And the other factor is how high you're going to fly. And, you know, in all honesty, you're going to want to fly as high as you can so that you can have better field collection. However, if your data requirements dictate that you need better feature extraction or better penetration, then you're going to want to fly lower so that you get those points per meter squared.
I'm sorry, Daniel, let me quickly interrupt you because there's this one question asking, so where does this point density number come from, or how is it calculated?
So it comes from the manufacturer, but it's well beyond what we're going to cover here today, but it's based on, you know, the pulse repetition frequency, the number of sensors that you have, the spin of the head, all of those factor into how much laser energy this particular LiDAR head can go out or can put out. So, but like I said, when we ever sell these, we actually provide these charts as a means to actually calculate this.
So I'm guessing that for each LiDAR sensor, the manufacturer sort of provides what point density can you expect at a certain altitude. Is that correct? That's correct.
And then depending on, there's one factor we don't show here because I'm trying to keep this as simple as possible. But like for instance, with Regal, you can actually change the speed of the mirror, which also would change the density, and you'd have a third set of charts to look at. But yeah, you would use a chart like this to determine what your settings are before you actually plan your flight. Does that make sense?
Yeah, at least to me it does. If the rest of the people listening don't know, I'm more experienced with mission planning, but not that experienced with LiDAR. So I'm also kind of, I'd say, acting on behalf of people listening to this because I get the chance to ask Daniel all these questions that maybe I don't fully understand regarding LiDAR specifically. And so I hope that somehow helps to bridge the gap.
Perfect. And yes, please, as questions come in, funnel them through, and as long as they stay within the context of what we're trying to achieve today. Otherwise, we can follow up and answer your questions in more detail afterwards. So yeah, and real quick in the chat, I'd love to see how many folks have actually used LiDAR. So if you've used LiDAR, can you put yes, LiDAR in there? And if not, just say no. That way we get a context of who's actually using this and trying to improve versus who's trying to experience this for the first time.
Actually, to me, it seems that some of you can't really access the chat because it's disabled for some reason. But to be honest, I can't really figure out how to enable the chat. I'm seeing that people are putting answers in the Q&A section. I was trying to see how can the chat be enabled in the settings, but can't really figure out. But anyways, yeah, you can put the answers in the Q&A section as a question, and so we can still see from there.
Perfect. So like I said, before we actually go and actually do flight planning, the biggest thing that you need to, especially with something that has a fixed RPM setting, is how fast or how much terrain do you want to cover and how high you're going to fly. And that all goes back to, what point density do you want to achieve while you're out there in flight. All right. If there's no questions, I'd like to move to the next slide.
Yeah, let's quickly see what questions are there. Maybe I don't think it's covered later on in the presentation, but there's now one question regarding maybe what drones can you suggest to use with LiDAR? Because Brian's asking, do you have LiDAR for DJI Mavic 2 Pro or Inspire 2?
So yeah, so right now, it is definitely a weight issue, and we talked about that IMU as, or that INS, it really is the weight of the system. So I know there's smaller systems out there that are used more for navigation, but when you're talking about survey grade, and you need that resolution, right now we're seeing it's Velodyne, which came out of the automotive industry. We have Quantigy that's showing a lot of promise, and Regal. And there's a few others that are starting to show promise, but those are the main sensor heads, and then whatever system they're going to integrate with. The smallest right now that I've seen is the DJI M200. The most popular right now is the integration on the DJI M600, and that's mostly because of the price point. I mean, it's for the cost, very, very reliable. However, we're seeing other vendors come in, other drone vendors come in and start to get some integrations in. Inspired Flight is one that shows a lot of promise, which is about the size of an M200 with a lot of capability, which is on a Pixhawk background. I know Microdrones has some setups of varying size, but you really are not going to see LiDAR mapping at the Mavic level or the Inspire level drone right now. It just can't support the weight.
Right. So as you said, mainly it's kind of a weight issue. So you just physically just need a bigger drone to be able to handle that payload and to be able to actually fly. Maybe some of the smaller drones, maybe they might be able to take off with the LiDAR payload, but they might not be able to cover the whole area because obviously the flight time is going to be reduced a lot.
Well, and it comes also down to, like, when we fly a larger drone with more rotors, you get a smoother response. And as we start talking about the planning and how to execute the flight, you really want to keep your flight smooth. I also use, or we're just starting to use, vertical takeoff fixed wing. And, that, as you can see here in this demonstration on the screen, you're looking at stall speeds about 12 meters per second. So you really want to be about 17 meters per second. The advantage to that is that you're going to cover a large amount of area, and reap the benefit of a vertical takeoff, and you can cover more area because you're able to loiter longer. So that would be a case of where you'd want to use that. But you're giving up a lot of density. And so for surveying, a fixed wing would be perfect. But if you're going to do, go ahead.
There's actually a question in the chat that's asking, do you see any increased noise or false returns in fixed wing systems when compared to multi-rotor systems?
No, right now, because of the altitudes that we're actually restricted to, every LiDAR cloud needs a little bit of cleanup, but when I compare a rotor to a fixed wing, they're about the same. And that really has to do, again, with the altitudes that we're at. If I was flying an aerial, in a helicopter or a fixed wing manned flight where I could be at 2,000 feet, there's more atmospheric interference and that kind of stuff. So right now I'm not, but if you are, I would love to hear it. So is there anything else here?
Let me see. So there's also a question asking what's wrong with single rotors. So I guess by this,
there's absolutely nothing wrong with single rotor. I've seen stuff. We carry Altus. Pulse has been using Phoenix LiDAR for quite some time. The advantage to being a helicopter guy, the advantage to a single rotor system is you can lift more, and it's a more efficient lift body. But the redundancy and the complexity of the system is the downside to that. So, when you make that decision, it's, how much maintenance are you going to do on your aircraft, and what are you actually trying to achieve? But no, there's a lot of folks using helicopters out there. So when I say rotary craft or multi-rotor, I'm talking about everything that can do a vertical takeoff capability.
Right, maybe now, so let's move on in the presentation, and then we can touch on some other questions later on.
Perfect. Okay, so while we talked about, going high is better for flight field efficiency, the downside to that and why you're seeing going lower, you'll get better response, has to do with something called beam divergence. And so with beam divergence, what that means is if you're using a flashlight or even in our case lasers, all beams want to expand at a certain rate. And so when you look at a manufacturer's schematic, especially like if you're looking at Regal or any of these guys here, they're always going to have a couple numbers, and so they're going to say, hey, we're going to be accurate to this level, let's say at 50 meters, and then at 100 meters we're going to be accurate at here at this. And this is talking about, your spot size. So you can be laying out a lot of point density, but then how dense or how certain are you of that point's location, and that has to do with what we call relative accuracy. So again, going back to your data requirement, if you're trying to get very, very precise, lower is better. If you're trying to cover a large amount of area for like a contour or general prep work, then you probably want to go higher. And so again, I leave this in, the spec sheets will have this, but it's one of the planning considerations that before you go fly or go plan, that kind of want to take this concept into account. And again, this will be something that you'll see in your spec sheet, not so much on those charts. So again, left this out. And so what you see here on this picture is one of the early collections we did. And you can see this is also a VLP-16, but we collected this at 60 or 70 meters. And you can see all your images are kind of a little bit mushy. I wish I had a comparison where if I had been flying at 20 meters, you would have seen each individual leaf on the tree just because of how close we were and how that beam hadn't had a chance to really expand yet.
Is there a certain limit to the altitude? Like, let's say when you're flying a UAV, how high can you go and still get reasonably reliable data?
Great question. And so that's going to vary from manufacturer to manufacturer, primarily the LiDAR head. So depending on the optics and the method of delivery, you're going to get different capabilities based on power and how well they're able to refine this beam divergence that we're talking about. So when you're looking at, let's say, Velodyne, its max range is about 100 meters. Now, that doesn't mean that you can fly at an altitude of 100 meters. That means that's how far the beam is actually reliable. So when we show you here in a few seconds, how we're actually planning the sweep width, you really are planning for the edges of your field of view to be under 100 meters, not necessarily your altitude. Now, when you're dealing with Regal, who right now in the drone UAS arena is probably the best product out there. Now if you're doing with a Minivux, I think it's 300 meters, which is a significant increase, and the resolution or how they actually measure the returns or the angular is much better. And if you're dealing with a full Vux, well, now you're dealing with an aircraft level sensor that can go to 2,000 or plus meters. So now you're limited more by your local nation's airspace rules. Or by the sensor itself.
Right, I think higher than 120 meters or 150 meters with the drone. So I guess this translates to about 4 400, 500 feet in the US.
That's true of the US and in Canada and a few other nations. They've all kind of resided around that to give everybody about 100-foot cushion between manned airspace and below.
But I guess there aren't really any permits that you, like, let's say if you want to fly higher and use drone to quickly scan an area, are there any ways how you can get some permits to fly like that? Or is it basically impossible?
That's going to vary from country to country. I can tell you in the US, you're going to have to get special waivers with safety plans and mediation. Or, and some of that mediation may require you not to be a drone pilot, but a fully licensed regular pilot. So yeah, it really is it's going to depend on the waiver process for the country that you're in.
But I guess when you're flying at a certain altitudes, you also need to take into account the maximum flight time of the drone. Because, I mean, when the drone is carrying a payload, already the flight time is decreased a bit. And you also need to take into account the time it needs for the time the drone needs to reach a certain altitude and then start the scanning mission and then come back.
That's true. That's very, very true.
Right. So do you have anything more to add to this slide, or shall we?
No, we can move on. This was more to show a quick concept. Okay. So now we're going to kind of get in. So now that we've covered all the theory, really would like to go more into a kind of a what, and then going into the how. And so what we're going to talk about here is really the beginning of the workflow. And so when we're in planning, we had talked about the general considerations as we're dealing with the bid. But for a lot of companies, you're not actually planning in your flight control software, so some companies are using, like, let's say Civil 3D, or there might be drone guys tend to use like Google Earth. Maybe they're using something like Carlston. But most work is construction work and environmental work, and stuff that's being done is done in some kind of other platform. But what's neat about UgCS is the ability to import that. And it's really important because as you're doing your planning, before we even get to LiDAR, what are the boundaries of your job site so that you can actually plan this accordingly? So that's the first thing. And the second part of that, so that you're not recreating work, is being able to mark features. So let's say you're a utility company and you're doing corridor work, and you're trying to, one of the nice things that if you have it is to actually have your towers already marked and those altitudes. So you can import those features so that you can plan around them, both as a terrain and an obstacle. And the last part of this is, even though LiDAR does not require ground control points to actually give it a reference to the Earth's surface, control is still a very important piece to validate that you're collecting at the right intervals, and in some cases to actually what we call registration, so that the data that you're collecting with LiDAR is going to match what you're doing with photogrammetry or satellite, or however you're going to actually set up that information. And so setting control points as part of your planning process and being able to inject those is really important, so that you can ensure that you're flying over those points in a way that they're going to be collected and seen. And then after that, if we look at the rest of this, you're going to fly an event, which is pretty straightforward. After you land, you'll download all that information, unless you have a streaming package. You'll take either your base station information, or if you're using a service, you'll fuse all that together to generate a cloud. You may have some cleanup software in there. At that point, it becomes what we call a raw geo-corrected point cloud. And then when you're in the analyst phase, this is where you would start to do the things like classification, which is identifying features that aren't the ground, generating elevation maps and contours, maybe pulling out three-dimensional objects, to the final point, which is to actually deliver a decisional made piece of data to your customer. So that's the whole workflow. And what I'd like to do right now is I'd like to show these guys, how do we do that inside UgCS and how easy this is to do.
Right, so let me just quickly open it up. Okay, so I'm going to leave the presentation on one side, and now you can see UgCS screen on the other. So basically, those not really familiar with UgCS, you can think of it as Google Earth that allows you to plan drone flight missions. And in addition to that, as Daniel already mentioned, you are able to import various data. So this can be a map overlay. This can also be a terrain elevation profile. And here I have imported some just KML files, which is basically kind of a region. And so, for instance, you can use this at the very beginning, so you can already see what area you're interested in scanning. In a similar way, you can import the same route as already an ready-made area scan or a photogrammetry mission. But of course, for LiDAR, you're probably going to want to go with area scan. And one moment. Yeah, so here in map layers, you can see what you're able to import into UgCS. So by default, we use Google Map Source, although you can also switch to Bing if you want. And here you can also actually import custom elevation data. So already here I imported it. So let's maybe focus in on that. So this is the data from a mining quarry that was imported. And I think here, if I now disable it, you're going to see that the area is totally different when this elevation is removed. So now you're able to see that the area it's basically flat on the map. So this is also where LiDAR comes into play. That Daniel, as we discussed before, that there's actually a possibility that that the data requirements, for instance, they might want like you need to have a certain point accuracy, right? But maybe before that, actually, in some cases, you might want to scan an area before that from, let's say, a bigger height, just so you get some ground control points, and then those you can actually convert into a 3D model, import into the flight planning software. So, and then you can actually use that data to fly a more accurate terrain following mission.
Correct. Yeah, and I'll talk more on actually terrain in the next couple slides. I mean, the key feature here that is being able to pull in what you've already used in your planning for your work, so you're not recreating the wheel, and you have better situational awareness before you go fly.
And the same actually goes with map overlays. So what you're also able to do is you're able to import map overlays so that, let's say if some area isn't really up to date, then what you can do is that you can take a drone with simply with a camera. You can do a quick, let's say, photogrammetry mission, and then you can generate like a map. And you can also actually use our inbuilt software, which is called UgCS Mapper for this. So then you can stitch the map together and also import it. So that way you can either choose to have map data or elevation data, or actually both.
And some people, like I deal with a lot with surveyors, and they would ask, well, why would I do photogrammetry and then LiDAR? And again, if you were trying to get those really high accuracy maps, or let's say you're doing 6-inch contours and below, and you're trying to pull out all those features, well, you're gonna have to fly pretty low. But by doing a simple photogrammetry mission ahead of time, well, that will get you what we'd call a digital surface map, which is all the features. So that increases your safety, and that really is important when you're flying around a high-price sensor like that. I mean, most people think that you can crash a $500 drone, but some of these sensors are significant. And so as a risk mitigation, this is a great way to protect your investments.
So maybe let's move on in the presentation.
Excellent. Okay, so now that we've covered a little bit about workflow and how do we import KMLs to show area and to be able to capture or lay out control points, the next thing here is talking about, okay, how do we actually establish the pattern? And so some systems allow you to restrict the field of view and some don't. When I first started doing LiDAR planning, I was trying to be very precise. And so I would program in, depending on the software that I was using, I'd program in the field of view. But then if I went over a terrain feature later in post-processing, you know, that was outside of that field of view because the terrain had changed, then I would have to go back out to the field. So what I started to adopt was to collect everything and then filter out later. And so that's just a matter of personal preference. I've heard people doing it the way that I used to do it. But again, just understand that, you know, most of these sensors, the way they're oriented, you either are collecting 360 around the aircraft, or if you have a down-looking sensor, they're going to have some restricted field of view. So the first thing to know is, okay, what is that field of view? And then to determine what that sweep width is. So I could show you a really, really crazy equation that would work with the tangent of theta to determine that. But essentially, you know, to keep it really, really simple, you know, if you are doing the tangent of 45, that means that these legs on the triangle are going to be 1 to 1. And so that a 90-degree field of view is going to give you 2 times the height will be your width. And why is that important? Why am I not collecting out to the full 180? And the reason being is that if you're doing survey work and you're trying to actually measure vertical, then the best returns are going to be as close to below the aircraft as possible. So that 90-degree field of view is what surveyors call a 1 sigma, or so that's the level of accuracy. When I start getting past a 45, I'm going to get more of my data or my LiDAR laser energy that's going to reflect in different directions. And that doesn't mean that the data outside of that 90 degrees of field of view isn't good. It's actually great. I use that information when I'm picking up buildings, and we call that side scanning. But for today, when we're planning out missions that for 90% of what we use LiDAR for in the aerial, we want to keep it within what we call the sweep width, or that 1 sigma. So for simplicity today, you know, to determine your sweep width, you know, I always go with a 90-degree field of view, and so whatever altitude that I chose as part of my off my point density chart, that's what I'm going to use for my height, and then I'm going to set my width as double that. So that keeps the planning very, very easy. But the second part of this is, and this is for area, is that, and where we also kind of differ from photogrammetry, is there's going to be some overlap as you're going back and forth in your area scans, or what we call swaths. And so if you're dealing with traditional photogrammetry using cameras, that overlap would be 60, 70%. So that little area that we see in my illustration here that's checkered would be pretty much the whole slide. With LiDAR, you really only need about 10% to give enough reference, maybe even 5%. I would say 10% just in case the terrain casts a shadow, and so that you can recoup that. Mind you, in post-processing, you're going to see that the LiDAR actually will have covered everything. But you know, the reason why you want to overlap by just 10% is that with LiDAR, you can actually have too much data, and it becomes fuzzy. And so really 1 pass with a LiDAR cloud or with a LiDAR sensor is all that you need. And you only need that 10%, which is only 1 meter or 2 as reference to hand off to the next feature. The other thing with planning this is we talked about, in theory, how important the inertial navigation system is. So how this works is that, you know, your drone is flying along, and it's collecting GPS points. And those GPS points, let's say, are at 1 second or 2 seconds or maybe half a second. And so it's saying, here I am, here I am, here I am. Well, with LiDAR, when you're trying to get really, really refined positional information, you're actually, collecting positions at tenths of a second, hundredths of a second. And so to fill in the gap between those GPS locations, you need the inertial sensor to say, yeah, you were here, but now you're here, and fill in those gaps. And so that's really why you use an inertial sensor versus like a terrestrial LiDAR scanner, but you put it in one spot and you let it sit there and it just stares at the cloud, or it stares at the GPS constellation to refine itself. With a mobile scanner, you need that inertial unit to predict. And so now that we know that about how the system works, when you're going to make a turn, well, now you've added a lot of inertia. So this would be like sitting in a chair, closing your eyes and spinning around really fast. You go to stand up, you don't know where you're at. So the way we do that is that in an area scan, we overshoot, or we call an overhang. We go past the area, and then we do a standard rate turn to come back in. And that allows the gyro or the inertial chip to keep up and stabilize out before we move back into our collection area.
So do you also do some IMU calibrations before the flight? Because I know some people who fly with LiDAR, let's say they do a figure 8, or either in manual mode, they can calibrate the sensor.
Great question, yes. And so every inertial unit's a little bit different in its capability. But yes, so every LiDAR system out there, no matter what salesman tells you, is going to do what we call a coarse and fine calibration. There are two different things that actually happen. So the coarse calibration is you turn on your LiDAR unit, and it's going to find all the constellations, typical boot up, and it's going to set your heading, because heading is really the most important thing when we're talking about acceleration. It's going to set it into a gross quadrant, so that it kind of knows, are you northeast, southeast, something like that. The fine calibration happens after you actually take off. And this is where we're trying to go from that very wide, I think I'm heading this way, to, no, I'm within 0.000 degrees of the heading that I want to be at. And so that's very important for positional accuracy. So depending on the manufacturer, there may be, and this has to do with, some of it has to do with software, some of it has to do with the way they measure the GPS signal, or how fast the chip actually refreshes. You may have to do a series of figure 8s, so they'll make a lot of turns so that the sensor can calibrate the acceleration and how fast that works. You may fly and do some cardinal turns. And there's some systems that can actually just do it by measuring the minute changes that the drone does until it gets to its location. So it depends on the quality of the sensor that you're dealing with at that time. But it's something that you definitely want to factor in and do before you actually do your area planning every time you restart your LiDAR unit.
All right. Maybe then we can at least try to make an example mission so people can see how would you create an area scan mission for a LiDAR.
Excellent. So let's use the best case scenario. And so we'll use 5 meters per second. You can go slower, guys. I find that though, for a lot of drones, if I go slower, then the aircraft doesn't have enough air over the fuselage. So I get some really weird heading vibrations. So I have found that 5 meters per second and above works best. But if you're the drone that you're using doesn't, perfect. Then we talk about turn type. So when we're outside doing that overhang, we want to try to do, is this spline? Yep. A smooth turn, okay.
Well, splines, basically, that's for Pixhawks mainly. So for DJIs, you would see either adaptive bank or a bank turn there.
Correct. Thank you. And then altitude type, and then height over terrain. So let's do, we're doing the quarry here, right?
Yeah.
Let's do 40 meters height over terrain, or AGL.
And so what would be the side distance now in this case?
So now that we're at, so let's say we're at 40 meters, and if we're using this 90-degree field of view, I know that my sensor for the data that I want to use is going to be 80 meters. So we're going to take 10% off of that. So we'll use about 75 as our side distance. You know, and like I said, you can be ballpark because we're going to have a little more on the outside of it, but it's good to kind of have a rough. And then
right now, sorry, now I'm getting a bit confused because here we have the flight height of 40, so side distance 75. So maybe you can explain how this formula is exactly used to get that. So here you just basically to get the because here there's the width, right?
right. So if I look at my chart over here, and I know that my width here is you know, is going to be 80 meters, then I'm going to want to move down 75 so that I get just a little bit of overlap on that. So I'm really only getting 10%, but I want to move down enough that I have a clean pass. Does that make sense?
Yeah, I'm just confused because like basically you can imagine that the drone's here, right, at the top. And so the side distance, it's actually kind of going to be this. So basically where this end of the triangle ends, this is going to be kind of the next survey line in the sense that this is the actual distance that now we're setting.
Say that again?
No, I mean in the sense that if the drone is here, right, at the top of the triangle, and the sensor is facing downwards,
Correct.
then so this height in our case is going to be 40 meters, but it's just
Correct.
that the sweep width is basically going to now be twice as the side distance is going to become twice as much.
Yeah, but you have your other sweep width. So if you had two triangles sitting over top of each other, you need to move this distance,
Okay, yeah.
this distance over. So that's why, you know, yes, if basically from here you need to move two of your heights minus 10% so that you have a new triangle that sits with just a little bit of overlap.
Right. Okay. So basically, the when the drone is going to be flying the next survey line, then essentially that beam is going to come somewhere right over here. So it's just going to cross into the edge.
Correct. Yeah, that's great. I'll actually, that's good. I'm going to add that to my teaching to show a side picture versus an overhead. But yes, because you just want just a little bit of overlap in your 1 sigma region. And that's how you use that over here.
Right. And then again, another question about the overshoot. So what overshoot would you typically use for a mission?
You know, again, it's gonna be specific on the IMU and how responsive it is. So let's just say if you're doing fine calibration and it takes you 8 minutes, you may want to get a little farther out so that you're holding straight. Typically for the ones, I use a lot of Novotel because I like their responses. And with them, I use about 10 meters, about 30 feet of overshoot. You know, and I make sure that 5 meters per second, you know, that's a pretty slow speed. But if I'm, you know, if I'm doing, let's say 20 meters per second, because I'm doing a really fast collection, I may actually increase my overshoot distance so that I'm a little more stable because, you know, I'm going to probably put a little bit of acceleration and inertia on the platform. But for 5 meters per second and a good IMU, I use about, yeah, 10 meters.
All right. Then maybe let me quickly put the points here.
And I would love to use a hard and fast rule, but it really depends on the hardware that you're using. You know, but usually with most of our folks, you know, within 2 to 3 flights of collecting data, they're like, oh yeah, this works, this doesn't work. And it's going to be pretty evident. Excellent.
So let me try to increase the area a bit now. Also, now it's easy in UgCS to change the direction angle. So we can try to set somehow like this.
and this is such for the people viewing this. If you guys are familiar with, like, let's say DJI Workstation Pro or some of the other ones here, you actually have to plan this all out by hand using some measurement tools, where UgCS does this all for you as far as your spacing inside the area. Not to mention, if you look at all the wave control points for the elevations, there's nothing out there that we have found like this, that makes it easy to start planning a solution like this, and gives you amazing access with your drone.
So if you also go here, then it's also possible to see the elevation profile of the route.
And that's really important for your quality control, for QCing your flight. To see if you're actually following, and you can actually follow along to see if you've covered all the features. I'll also say that, for some of the folks that are using like Altus or that have to fly with Mission Planner, a lot of our folks are using UgCS for this kind of planning feature alone, and then exporting this file so that you still get all the benefit of UgCS, but still are able to integrate in with the flight control system of the drone that you're using.
And so one question that I have from seeing this exact mission is that you can see there's like a wall here in the quarry. So how would the sensor handle this? Because I'm assuming that on this exact survey line, then the sensor kind of hit the wall, right?
Right.
But whereas this one, it would kind of get a bit more data, but maybe here, like where you have these kind of multiple walls or falls, I'd say, then you're not going to get this data in this corner. So maybe this somehow relates to the field of view that, as you mentioned, that basically most sensors, as I understand, they get data from 360 degrees, but just in post-processing, you can adjust this field of view.
And this is a strong case for why you don't restrict the beams of your sensor or the field of view. So like, for instance, and this is a great question and a great example, kind of gets me excited. We have a client that we're working on right now that we're taking an M200 with a Quantigy. And what he wants to do is, he's actually using LiDAR to measure not just the top, but also the underside of these structures. And so with it, we're actually able to actually measure up above the drone. Even though the drone is there, I can still see 10, 15 degrees of elevation, what we call side scan. And that's what you're going to see here, is that when I look at this, I may shrink my spacing just for symmetry. So there's no hard and fast on the spacing in some ways. But remember, we said our max distance is, in this case, if I was doing a Velodyne, let's say 100 meters. Well, I'm well within 100 meters, and I can use that side scan feature. And in post-processing, I may not clip it. I may use that side scan to pull out, because it's still accurate. It's still within, that tight field of view. It's just I've turned my triangle sideways. So it's very valid to get returns like that. Does that make sense?
Yeah, and actually we also have a question of, could you give an example of using UgCS as well as LiDAR in a urban environment? So maybe you can add a bit more on this.
Well, so in an urban environment, again, it depends on, what is your data requirement? What are you trying to achieve? And so if you're just doing mapping, you're going to probably fly high. But if you're, let's say, trying to do feature extraction, then you're going to want to put your object in this field of view, but in such a way that you can use more than this 90-degree field. At that point, now you can start to, when you get your data, you're going to get three-dimensional data of that building, and you'll classify that, those points that are the building, and you can pull that building out and put it into, let's say, Revit or any of the AutoCAD to actually put that in for a CAD drawing. So, while you're never going to get the accuracy of a terrestrial scanner, because a terrestrial scanner will measure down to the millimeter level. For a rough level of design, a mobile scanner, like a drone mobile scanner, can suffice. Does that make sense?
Yeah, and one thing I also wanted to mention is that when you're flying in an urban environment, one thing UgCS actually supports is we support 3D building import.
And that's one of the features we really like, is because we can take a LiDAR cloud, pull out a building, and then re-import that back into UgCS. So if you were, like we were talking about utilities, we could fly a utility corridor for what we call reality capture and capture the towers, and then put those into UgCS, and it increases our safety tremendously because now we know where everything is.
Actually, maybe since we're on the topic, I'm going to try to quickly import a building just to kind of show how it can be done and how the building is displayed here. So all the import in UgCS, it goes through the map options here. So here, then you need to go to map layers, and then you have 3D objects. Then let's try to add the building. And let's upload. Okay, now let's focus in on it. So the good thing is you can add multiple building sources. So you can have one source that has, let's say, buildings for one city, then another source that has buildings for another city. So you can see an example of how the building would look. And this is taken from some default data set.
And you can quickly see, if I was planning or even when I'm flying, this just increased what we call our situational awareness tremendously.
So of course, not always you might be able to get these building models beforehand. So yeah, I suppose in some cases, what you might want to do when flying in urban environments is, as mentioned already earlier, you might want to fly at a higher altitude at first, and then kind of get, because you might have some other obstacles there, some other, let's say, light poles, etc. And
you can also use, depending on the currency of the data, you can also go with satellite or some of the vendors out there. So if you're a construction company, you're probably going to go get something that's been collected a little more recently before you go do something more precise. And for the readers here or the viewers here today, this is a lot of work, but the reason why you do this is if you have jobs that you're going to be going through that same job over and over and over. A one-time capture, this makes no sense. But if you are doing repeated captures, this is definitely something you're going to want to do.
All right, so maybe let's move on further in the presentation.
Correct. We're kind of running a little over.
Yeah.
Well, and we can, we've covered a lot of the how ahead of time. So we talked a little bit about terrain follow, and you saw us actually use the side profile, and you can see it over here at our quarry. And we talked about not all sensors being created equal. So we have two sensors here, and as I showed you, this is we call it our mini package, but so it's an M200, and we have on here a VLP16. It could also be a quantity M8 in this particular configuration. And we had talked about, with beam divergence, really this sensor its best altitude is about 40 meters, maybe 30 meters. Even though the range of what it's capable is 100 meters of max distance. Where if we have the VUX here, which is on the Harris 6, which is a hybrid drone, flies about 2 hours with that sensor payload. Now you can actually, I forgot how far it is. It's like 2,000 meters or something like that. But now you can fly higher. It's much more forgiving. Well, the difference would be that this the Mini here has a higher return on investment. It's cheaper. You can use it for 90% of the stuff out there. but it's not going to give you as nice of a cloud. To maximize that potential, it's all about how you're going to fly. And so you can fly lower, and using that terrain follow to get all those features, where that same sensor for the VLP, or sorry, for the VOX, you can fly higher because it can actually pick up all those reliefs. So when
right. So basically, with the more expensive sensor, you're able to fly higher and essentially cover more ground in one go. But you have a cheaper sensor, at least from what I understand, is that you can still get a reliable data. It's just that you might be forced to fly a bit lower to capture it.
Well, correct. And I guess what I'm trying to say is, let's say I'm flying over a valley, and that valley drops down 50 meters, and I'm already at 40 meters of elevation. With the VLP, I should drop into the valley because I'm already approaching, very, very closely approaching the end of my sensor limit. And so with beam divergence, I may not be as accurate and true to where the placements of that relative points are. Where with a VLP 16, with a VOX, which is the lower one, I don't really care, because my sensor limit of how far I can see accurately is better. And so terrain follow comes into play here, that I can actually use a more affordable sensor and get a quality product, but I just have to change the way that I fly. And then of course, the last piece of terrain follow is I have a lot of people that have not followed my advice and don't use UgCS, and probably within 3 to 4 months they call me up where they've flown right into the side of a hill, where they use something that's on a tablet, and they don't take into account to terrain, and it smacks right in, and they lose that sensor. So controlled into flight is really important, and for everybody here that's going to be in the US or in Europe, beyond line of sight is definitely coming. And I do a little bit of consulting to the FAA on beyond line of sight, and one of the considerations that part of it is, well, hey, how do I keep from smacking into another aircraft? But the real big issue is, how do I keep from actually colliding into the terrain, and how am I aware of that? So beyond line of sight is a twofold problem. Partly is how do I keep the air traffic safe, but the other part is how do I keep pedestrians and the ground safe. And by doing terrain follow and having that in your program solution, you're much more likely, or as the laws comply, you're going to, or evolve, you're going to be much more ready for beyond line of sight when that comes as well.
But I guess still, you probably, as an operator, have to think about getting some form of insurance for the drone and for the sensor, not knowing how expensive it can get.
Yeah, and I would love to say that the insurance company would give you a discount because you have this feature, but they're not that sophisticated yet.
Unfortunately.
Let's go to the next slide. Okay, so you already covered it in UgCS here, but we know that UgCS pulls its information off of Google or Bing or any other server that has DTED or elevation information on it. But if you're questioning it, or you're dealing with industries that your terrain is changing, so mining is a good one. I keep going back to utilities because most utility companies may know where their towers are, but they don't know how high or the exact location of them. That's always an issue, or even unknown features that kind of crop up. So if you're not going to an aviation source that gives you more current obstacle information, then being able to import that information is important. And so we showed that here earlier, that for conditions where you don't have elevation data, or it's uncertain, or there's things that aren't really well defined, being able to import your own elevation maps and your own obstacles is a huge safety increase.
Actually, no, speaking of imports, we actually have a question that maybe we can address right now. So this question is regarding, so first off, what formats can be imported for existing terrain and buildings? Then also, so how do you capture that information with LiDAR, or can photogrammetry be used? And also, how do you format that data from LiDAR or photogrammetry so you can import that on top of UgCS? So maybe I can answer the first question, and then you can answer the next. So what formats can be imported for existing terrain and buildings? So basically, the building file that you want to get a KMZ file. So you can get this either from data, or you can get this from the internet. So in some cases, you can use, let's say, Google Warehouse, and you can get this data from there. But for LiDAR applications, I suppose you actually are able to create this yourself. But then this brings us to another question. So this question is, so what software can you use to actually make this data, or let's say to gather this data from the LiDAR and then convert that to these formats? So, and also, yeah, so for buildings, it's KMZ, and for terrain elevation, it's TIFF file, so .tif.
Okay. Yeah, I mean, the TIFF file is pretty common. And so there actually is a bunch of different software so that you can use. But let's go through LiDAR, and then the big thing here, guys, is that, you know, once you have produced your point cloud, and it doesn't matter if it's LiDAR or photogrammetry or something else that's, you know, once it's in tabular form, it's easy to convert. You know, so my team actually likes Global Mapper, and you know, made by Blue Marble. And the reason being is inside the Global Mapper suite of tools, they have and I'll tell you, for the price, I would buy it just for this. And by the way, I make no money off of this. So this is just, honestly, I just really love their product.
It's free commercial for them, basically.
Exactly. And I'm sure I'll hear about it later. But I'll tell you why. I mean, for $750 to $1,000, which some guys are going, oh my God, you can convert between 250 different file types. And that's in itself already a huge capability that's worth it compared to other softwares out there. But yeah, you can go into Esri or some other GIS programs and download or export out of that. But if you just needed to straight convert, I would look at Global Mapper. A TIFF file is actually a pretty common file. And then if you're in, let's say, Revit or an Autodesk type format, you can actually download the other formats. So, but again, for me, if I had to give you just a straight answer of one-stop shopping, I would look at Global Mapper as the tool to convert.
Right, and and another question actually is, so do you capture this information that you can later import? Do you capture it with LiDAR, or can photogrammetry be used as well?
Yeah, so again, once you get into point cloud format, you can use, like I said, you can use photogrammetry, you can use LiDAR, you can use synthetic aperture radar. Once you have those points in a point cloud, you can use any of that. It's all relative data. The one thing, like I was at the International LiDAR and Mapping Forum just yesterday. I flew in late last night. But one of the things we had talked about is, which digital model do you want to use? And so this is probably a good point to bring up, is like, once you collect your data, whether it's LiDAR or photogrammetry, you know, a lot, like if you get information off of a satellite server, they'll probably already be in a digital elevation map. And so a digital elevation map removes all the vegetation, all the buildings. All it is the base elevation of the dirt. And you know, for flight planning, you know, at that point now you have to factor in the trees and the vegetation. What's really advantageous is, if for using photogrammetry or LiDAR, it's to leave it in what we call a digital surface map. And what that means is it is the topmost elevation of any feature on that surface. And so if I had to give guidance on this, I think I would say that you know, try to get a digital surface map that's uncategorized, unfiltered over trying to get a digital elevation map, which only has the terrain elevation. But other than that, you can use any source to get that file and then convert it into a TIFF. That makes sense.
Yeah, and also I guess maybe you can add that if you're kind of considering that you want to use your drone to gather the data, maybe if you, let's say, have one drone that has the LiDAR sensor and another drone that just has the camera, and maybe you just want to kind of go over one time just to get some initial data, then maybe it's actually a good idea to use the drone with the camera first and do a simple photogrammetry, just because in case there are any obstacles or in case something happens, then usually the drone with the camera, you can use it. Usually it's a lot cheaper than the drone with the LiDAR system. So let's say if you happen to crash a Phantom 4, for instance, it's not going to be as big of a loss if you, let's say, happen to crash an M600 with a LiDAR system on it.
Unless you're doing stuff with a 100 megapixel camera.
Yeah, that's true. Actually, another question we had is, are you able to smooth out the terrain following? And this is actually a very good question. We didn't touch on this.
Demonstration.
Yeah, so here in UgCS, actually, we do have the AGL tolerance parameter. So previously it was set to 3 meters. And now you can see it when the mission is calculated, then you can see it's kind of quite rough in a way that it changes the flight height quite often based on the altitude data. But you can actually increase this tolerance. So if you increase it, let's say, to 6 meters, then here you can see you're not going to get as many points. If you go even further, let's say to 8 meters, then you're not going to get as many kind of waypoints in the middle. And so the flight is going to be a bit more smooth.
Yeah, and the 2 times we use that is one, when I'm dealing with, I may increase my tolerance if my features, I had to be closer to the ground, but then I like my aircraft to fly smooth, but also depending on what the autopilot system is, like if it's DJI A3 versus a Pixhawk, the number of control points that it's able to store may become an issue. So playing with that number, depending on what hardware you have, is kind of important.
Right, because some of them, they're limited to, I think, 99 waypoints, at least some of the autopilots. So by playing around with that, you're actually able to load these missions. And actually, I also can mention that in case you do have quite a large area that you want to cover, that you want to fly, actually, UgCS, we have the function to change the battery in the flight. And what this means essentially is that, let's say you can do these first 2 survey lines. Then after that, you can return the drone back, and then you can re-upload the mission just by changing the starting point. So let's say at first the starting point could be somewhere here, and then you would fly these, let's say, 2 survey lines, and then you could actually change it so that when it comes back, it just starts the mission here. Of course, this area is quite small, but with some bigger areas that might come in handy. Actually,
okay.
we're kind of
we're running out of time.
Probably move on because we already used a lot of time. So maybe let's. Can I move on to the next slide?
Please.
Yeah.
Yeah. No, this is good that we had a lot of good questions, and so so with this, I hope that this was presented a little bit more insight into what the difference is between LiDAR and photogrammetry and the planning considerations. And for the folks that are already using LiDAR, I hope this helps get you better clouds. But I'm also going to make a quick offer here, and we talked a little bit about LiDARuniversity.com. So if you want to learn just some basic information, like I said, we have a free course on LiDARuniversity.com that goes over the technology, the different use cases, the data products, and what have you. But for folks in the US that want a hands-on experience to kind of go through this workflow, talk about UgCS, but then also get your hands on different sensors firsthand and see the planning and go out in the field and actually do this. We have a partnership with Kansas State University that has a specific UAS main track. And so our next offering will be April 15th or 19th, excuse me. And we should have that up on events on LiDAR University if you would like to attend and get something more in depth.
So I saw that there were quite a lot of questions actually regarding specific hardware. What should you use? Let's say, what drone platform should you use for LiDAR? What LiDAR sensor? So I suppose if someone's interested in that, then this is actually a very good offer for them.
Exactly. I mean, like I said, it's very rare. Well, we'll put it this way: no manufacturer is going to go out there, or that we know of right now, and we work with a lot of them, to show you a side-by-side case in one sitting. I mean, we do demonstrations in our own company. If someone's going to purchase or wants to purchase, that we'll bring out one sensor head. But this is an opportunity to see, even if we bring out one sensor head, we're going to show you all the data sets in comparison, so that you know what the difference is between a VLP-16 and a 32 and a Quantigy M8 and a Regal Minibux. We can show you those sets and explain, because I know that for everybody here, if you're looking at Regal data, it looks beautiful. It's beautiful. It's also a very expensive sensor, and 90% of what you need in most land mapping situations is far below that. So for folks starting out, or wanting to, or for firms that want to get the max return on investment of a piece of equipment, this is a chance to show you the trade-offs of whether you want to purchase a low end or a high end, or purchase a low end and then rent a high end, and all of those strategies that come into business. So that's why we have this here. So yeah. Any other questions that you see on that side?
All right, let me see. I'm not checking the Q&A section. I think, yeah. So basically, I think now we can actually move on to Q&A part. So the official webinar part is over, but if you have some questions that, I assume some of you might have a lot of questions regarding use of LiDAR and use of UgCS. So if you have any of them, just put them in the Q&A section, and then we can go through them now and see if we can.
You know what, let's make another offer. If this was useful and you think that this software and this may be something for you, I'll tell you what, if down at the bottom of the slide here, I have info at Modus AI, which is our company. Let's say for the next 2 hours, if you send me an email and saying, I would like UgCS, why don't we offer it at a discount? So we'll do it at, we'll do that at $560. We'll throw in our online training to onboard you onto that, and I'll give you an hour worth of use case. So if you're trying to do this with LiDAR or a particular use case, I'll give you a free hour of consulting, which is about $1,500 normally for the people that I actually do this for. So if this is something that would benefit you, and you think this is of value, I'll give you that special promotion within the next 2 hours.
Right, so if someone emails you in the next 2 hours, they're going to get basically free consulting on using drone with LiDAR.
Correct, along with the software to show you how to go and lay this all out for you. So I'll actually build your use case for you.
All right, so let's see what questions we have here. So we have one question that asks from Bart, can we do LiDAR and photogrammetry at the same time?
Great question. Depends on the drone, and it depends on the software that you're going to be using, but yes, you can co-capture. So some systems out there will have it actually integrated in, or you can do, we'll have it integrated in that the INS will actually meta tag the camera data along with the LiDAR data. You can use, like for instance, DJI, if you want to buy just a sensor head and use a DJI camera, you can, but you're going to have to probably move a little slower. But the higher end systems, you can do, depending on the weight and what you're using, you can do LiDAR, and you can capture single camera natter. You can do dual camera offsets, and you can do a 3-camera configuration. And with that, it depends again on your use case, and I really didn't get to too much detail on it. But then you can, with that, you can colorize your data into what we call RGB point clouds, which make great presentations. And it's pretty easy to do. For the ones that, I'm not a big fan of the LiDAR manufacturers that say they can stream. Streaming is good if you want to see how effective your collection was, but you really need to put it through post-processing to make sure that your data is accurate. However, colorized point clouds help you later in post-processing to identify features for classification. So that's the real reason why, from an analyst standpoint, you'd want a colorized point cloud. I hope that covers it all in one can.
Yeah.
That was a lot.
Okay, so let's see what other questions. So one was, what's your map provider? So by default, as I already mentioned, UgCS uses Google map provider, so it's Google Satellite. And you can actually switch. You can use Bing, or you can actually use your own maps. So if, for instance, you can switch to Bing maps, so you can see that the map data you get is a bit different. So in some cases, you actually might want to switch, because obviously not all this data is gathered at the same time. So if the terrain is changing and you just need to change the default map, then you can kind of use this to see which one is more accurate and which one is more up to date. Let's see what other questions we have. Do you know what rotational speed the fixed wing in the sample is using? I guess this was probably referring to the one of the slides that had the fixed wing. So what exactly is, I guess, rotational speed is the speed of the mirror in the sensor, right?
Well, this set, the HDL32 doesn't have mirrors. It has a laser array, and for this particular example, this is set at 1200 RPM. Yeah, because you're right. For Velodyne, you can change the RPMs as well, and that's a different table. And generally speaking, for what we do, what we found is that we just keep it at 1200 RPM. So I haven't found a good strong use case yet to change the RPMs for that.
So another question is SRTM data at the treetop level to ground or something in between? Actually, I'm assuming it's at ground level, at least should be. So the default elevation UgCS is using, it is SRTM4, I think. So I think it should be ground level elevation, or maybe mixed, but definitely not treetop, because you can see there's where the trees are, it's kind of the same level as the ground. So, okay, question. Do you have a training provider for UgCS in the UK or somewhere in Europe? Well, I mean, we ourselves are actually located in Europe, in Latvia and Riga. So if you want, we can actually do training for you, or we can refer you to one of the resellers that we have in the UK. So another question, do you find there is no appreciable loss in accuracy using rotational speed of 1200 RPM versus 600 RPM? So maybe Daniel, you can tackle this.
I haven't honestly looked to see if there's, I mean, I haven't done the comparison of the rotational speed. Every time I've looked at the rotational speed, it's been more about the point density. And again, the comparisons we've done with the sensor is more based on altitude to try to quantify beam divergence. But no, I have not looked at rotational speed versus accuracy.
So another question, RTK on drone control or just the LiDAR device?
That depends on the manufacturer. So most of the sensor operators out, or payloads out there, tend to be independent of the drone, unless you're buying something very, very specialized. Most of the sensor integrators out there build their system so they can go on anything. And so, like early on when we were developing, we tried to use the DJI GPS system, and let's just say that it was totally locked out and it was used in the wrong timing, which is a huge issue. So you can find somebody out there that will do a specialty and that are flying, with a high-end INS system. But like I said, like Yellowscan and Phoenix and LiDAR USA and Regal and Trimble and all those guys are all building it separately with their own inertial navigation system built onto it. And the other question would have to be, because I heard RDK, my personal experience has been that PPK tends to be more accurate. However, when you're using RDK, it allows you to see more real-time visualization. So if it's important that you see some colored pixels and you want to run the risk of losing that signal and having to capture later, RDK. But if you really want something precise and you can do it in post-processing because you have a little bit of time, then PPK, because you get the whole, you look at the whole flight and you look at the whole correction, so you get a better refinement of your accuracy.
All right, so then another question that's actually quite interesting is about surfaces. So question is, how does a plastic or reflective surface like windows affect LiDAR? And I suppose this also touches the subject of flying LiDAR over water, because I guess water also doesn't really reflect.
Very popular question. Well, first off, these sensors right now, with the wavelengths that they use, do not penetrate water. So water and I'll get to plastics in a minute, but water absorbs light completely, and so it shows up as a black surface in your cloud. So windows, I haven't really looked closely at windows specifically. I know we can penetrate them to some degree, but then it comes to how much of that's refracted versus how much is reflected. However, like streets and roads and stuff like that, the blacker it is, the less you'll still get returns, but the less. But then I can tell you that like the reflection, like road markings come up beautifully because of its high reflex index, and really the material in between, like dirt and vegetation, varies. I don't have an actual index myself to kind of give you guidance on it, other than it does differ. And I'll tell you that metal will reflect much, much better than wood for the same size. So we were giving that example of the power lines. If I was to do the same kind of study for, let's say, forest management, a 3 centimeter branch would reflect much less than a 3 centimeter power line. And so I'd had to plan for that in my collection. So I hope that answers it in some degree, but I can't give you a firm reference on that.
So I suppose, like, let's say when you're flying over some, like, factory buildings with metal roofs that in some case might be reflective, you're still getting this data back, right? Correct,
you are. So even with a black roof, you'll get a few points. You're just not going to get very many. So with road work, we get, we had to fly a lot lower with roads. So a lot of DOTs are starting to look at collecting well beyond the berm. But when we do collect on roads, we fly lower so that we get some of those points back.
Actually, also, how do you deal with, let's say, when you have to use LiDAR over some road infrastructure, how do you deal with cars?
Well, one, you try not to have them there. It's a popular question with the construction guys, whether it's cars or their equipment or any kind of resource laying around waiting to be used, that, they go, what do you do about that? And I mean, some of the LiDAR best practices is first, try to collect when they're not there. So if you can fly early in the morning or you can fly at night, so that, they're not there at all, that's preferred. If you do fly at a time where you have to fly at a certain time of day, at that point, now you're going to take care of that in post-processing. And so your analyst is going to open up your cloud and you're going to see the cars, and you're going to, using like for instance, Global Mapper, you're going to go in and actually classify the car as noise and filter it out of your solution. That's the power of a point cloud. You can do pretty much anything you want with each pixel or each point.
And actually, another question I have is, how much time does it usually take to process the data?
Again, it depends on what you're trying to achieve. In the example that we had, I can get a raw point cloud within just a few minutes of landing, where that same thing in photogrammetry would take me a couple hours. But turning it into usable, and it's going to be the same, or how am I going to put this? Once I have it in point cloud form, whether it's photogrammetry or LiDAR, now the points to filter it to, let's say, a DEM or a flood map or a solar aspect array or any of these decisional products are going to be about the same. The only difference would be the amount of cleanup. So photogrammetry, you're going to spend more time cleaning up structure, or let me rephrase, vertical structure, because photogrammetry does very well at the XY type of, because that's how it does it. Compares features on the ground in the XY plane. You use LiDAR to use when you're trying to do anything in Zeta or the Z. That's the real strength of LiDAR. So you'll do less cleanup with LiDAR. But once you're in that zone that you have a point cloud, then the steps it takes to process it into decisional stuff is about the same. And it will vary. It will vary based on what you're trying to do.
Right. Then we have a question that's, so Robert is asking, will there be a link emailed to participants to see the video? So yes, I can say that this whole webinar is going to be recorded and we're going to post it on YouTube. So later on, we're going to email this to all the participants so you can get, you're going to be able to replay it if you want to. And actually, I'm saying we're not really getting any more new questions. And since we're already kind of used quite a lot of time, more than planned, actually, maybe we can actually, it always happens like that, I think. But then I think actually we can maybe call it and kind of end the webinar here. So,
Great questions.
Yeah, so Daniel, I want to thank you again for joining us. I want to also remind everybody that if you are interested to get more information on LiDAR, then you can email Daniel at info@modusai.com, this address that's right here. And if you email Daniel within 2 hours, you're going to get sort of into this offer of getting a free LiDAR training for I think it was an hour, you said, right?
So they'll get UgCS at a discounted rate. We'll give them the online training that we use to onboard you onto UgCS, and they'll get 1 hour of consulting time to build out a use case in UgCS flight automation to achieve work.
All right, sounds great. Okay, so I guess then maybe we can end it. And so thank you everybody for coming to the webinar. Thank you for listening. I hope you enjoyed it. As I already mentioned, if you want to see it later on, then you're going to be able to get access to the video and see it on YouTube. So I guess that's it. So thank you once more, and I can only wish safe flights for everybody.